Hi there. My friend here is still pretty upset about that AFC Championship football game back in 2015. You know the one I'm talking about, right? The one that's now affectionately called Deflategate. It was a game between the New England Patriots and the Indianapolis Colts, and the Colts accused the Patriots of intentionally deflating their footballs in order to gain an offensive advantage. Now, I'm a Patriots fan, but I do not condone cheating in order to win football games. As a statistician, I've always wanted to actually take a look at that data myself. Are you in? Let's get to it. The Wells Report is the official document from the NFL's investigation of the Deflategate scandal. Here are the data that I have taken from that report as I have coded them into the statistical analysis software, SAS. The pressure per square inch, or PSI, of 11 Patriots footballs and 4 Colts footballs were each measured at halftime by 2 separate officials. Thus, there were a total number of 15 footballs examined. Additionally, the Wells report indicates that official number 1 used one gauge to measure the Patriots footballs and a second gauge to measure the Colts footballs, while official number 2 used the second gauge to measure the Patriots footballs and the first gauge to measure the Colts footballs. So here I have created a new dataset that modifies the original dataset in which I have now created an additional variable, gauge. At first, analyzing this data may seem very straightforward. We have 3 fixed factors that could affect the PSI of footballs: team, official, and gauge. Unfortunately, due to the way the measurements were taken, we cannot evaluate the effect of official as it is entirely confounded with the team by gauge interaction term. To examine the effects of team and gauge, you may be tempted to write your model this way. However, this would be wrong. Why? When you run the codes written this way, you will see that there are 26 degrees of freedom for the error term in the f-tests. Because only 15 footballs are measured, we know that the total number of degrees of freedom for investigating the effect of team is incorrect. The total number of degrees of freedom should not exceed 14 total for this effect. When the codes are written this way, SAS is treating the data as if there were 30 footballs, not 15 footballs that were each measured twice. If you use the p-values produced from these codes, you are committing one of the most common statistical errors, pseudo-replication. Pseudo-replication occurs when you treat non-independent observations as independent, which results in giving your test more statistical power than it should actually have, which means you are more likely to commit a type 1 error or falsely rejecting the null hypothesis. In order to avoid making this kind of statistical error, you need to understand how many independent experimental units you have, thus knowing how many true replicates you have, which will dictate how many degrees of freedom you have. In this case, the 2 measurements made on each football are subsamples. One way to correct for this is to take the mean of the 2 measurements so that you only have a single PSI value that represents each football. Looking at the output when the data are analyzed this way, you will see how much less power this test has by looking at the f-value for team. When it looked like we had 30 footballs, the f-value was much larger, 62.49. Now the f-value is only 33.89 when having only 15 footballs. In either case here, the f-value is large and the p-value is very small, less than 0.0001. Thus, in this particular case, the conclusion we would come to would not change, but this will not always be the case. Something else you may have noticed is that by analyzing the data using only the means of the subsamples, we lost information. By taking the average of both measurements, we have lost any information about the 2 different gauges that were used to measure the footballs. Also, we lost a level of precision in the estimate of the experimental error. For these reasons, the data should be analyzed properly as a split-plot design. We do this by identifying for SAS what the level of the experimental unit is for the main plot factor by identifying the additional error term required in the random statement. In this case, the main plot factor is team, and the independent experimental units are the 15 footballs. There are 11 true replicates for the Patriots and 4 true replicates for the Colts. Now you can see in the output produced here that we have 2 experimental errors, which I will call error A and error B. Also notice that not only do we have the same information we had for team that we got in the previous analysis, but we also have information about gauge and the interaction term between team and gauge. Once again, we can check the output to make sure we have not committed pseudo-replication by comparing the degrees of freedom reported against what we would expect them to be. The total number of degrees of freedom we should have for this ANOVA is 29. We know this because the total degrees of freedom will be the total number of data points minus 1. But we also know that the total number of degrees of freedom we have for the main plot factor, team, is only 14 because we only have 15 independent footballs. Estimating the effect of team will cost 1 degree of freedom because team has 2 levels. Therefore, there are 13 degrees of freedom left to estimate error A, the error term for the main plots. Based on this information, we know that the numerator degrees of freedom for team should equal 1, and the denominator degrees of freedom for the F-test for the effect of team, which is the ratio of the mean squares of team over error A, should equal 13. Looks good so far. We have more replicates for the effect of gauge, as each gauge was used independently 15 times for a total of 30 data points. It will cost 1 degree of freedom to estimate the effect of gauge, and 1 degree of freedom to estimate the interactive effect of team and gauge. A significant interaction would indicate that the difference in football inflation observed between teams is dependent on which gauge was used to measure the footballs. So if we had a total of 29 degrees of freedom to spend for our analysis, and we spent 16 on the estimation of all of the other terms in our model, this leaves 13 degrees of freedom for the estimation of error B. It looks like we are all good. Now that we know we are no longer committing the error of pseudo-replication, there are still a few other things we need to do before we interpret the rest of the output, and that is to check our statistical assumptions, specifically the normality and homogeneity of variances assumptions. This is done easily in proc mixed by adding the option residual to the model statement. Residuals are the differences between the observed values and their expected values based on the statistical model. We examine the assumptions on the residuals so that we can pool all of the data, otherwise our sample size would be too small to examine the assumptions. What we are looking for in the plot of residuals is a lack of a pattern such that the range of residual values should be the same across all predicted means. Based on our plot of conditional residuals, I am concerned about the homogeneity of variances assumption, as the conditional residuals produce a horn shape. When looking at the unconditioned residuals, it appears that there is a wider range of residual values among the Patriots footballs, which have the lower predicted means, regardless of which gauge was used, compared to the Colts balls, which have the higher predicted means. The good news is that even though it appears our data violate the homogeneity of variances assumption, we can tell SAS to estimate a separate variance for each team's balls. This is done using the group option within the repeated statement. You will see in the resulting output that there are now 2 separate error B terms, one estimated for each level of team. When looking at the fit statistics, it appears that our new model that uses 2 separate variances is a better fit, but to confirm, we will re-examine the plot of conditional residuals. Indeed, it looks like we have eliminated the troublesome pattern in the residuals. Also, looking at the right-hand panel, it appears that there is no significant departure from normality among the residuals, so we can feel comfortable interpreting the rest of the results. Since there is no significant interaction term between team and gauge, it means the difference between measurements that was due to using a different gauge is the same for both teams' balls. It is interesting to note that there was a significant difference between the two gauges, such that measurements taken with gauge 1 were significantly lower than measurements taken with gauge 2. Looking at the means, you can see that the Colts balls were within the regulatory limits for PSI, measuring 12.53 PSI on average. The Patriots balls were not within regulatory limits and had significantly less PSI, measuring 11.3 PSI on average. However, another important piece of information that I haven't covered is that the Colts claimed their balls began at 13 PSI and the Patriots claimed their balls began at 12.5 PSI. So both teams' balls deflated between the beginning of the game and halftime when the balls were checked. So then, the real question should be if the Patriots' balls deflated more than the Colts' balls. So what about physics? Could the starting PSI of the footballs affect the rate of deflation? Maybe. But I'm no physicist, and I don't know the answer to that question. So forget about physics. This is a statistics lesson. If the balls for the Colts had half a PSI greater inflation at the beginning of the game, then the hypothesis I want to test is whether the difference in PSI between the footballs at halftime is significantly greater than 0.5 PSI. To do this, I will ask SAS to produce a 90% confidence interval for the difference between the two teams' means in the LS means statement. I have used the option CL to ask SAS to provide the lower and upper confidence limits for the mean difference between the Colts and Patriots balls. I have chosen 90% as opposed to the default of 95% because I have a one-sided alternative hypothesis. I can use the option alpha to make this indication. Now, if 0.5 falls within the 90% confidence limit, I will fail to reject the null hypothesis and conclude that the change due to deflation during the first half of the game was the same for both teams. Looking at the result, we see that the difference in PSI between the Colts and Patriots balls is significantly greater than 0.5, and in fact may truly be anywhere between 0.81 and 1.65 PSI difference. Therefore, either the difference between the inflation of the balls prior to the game was also greater than 0.5 psi, which we actually do not know because the balls were not measured by the officials prior to the game, or it appears someone did tamper with the Patriots' balls by deflating them. I have not read the Wells report in full, but we know that the latter is the conclusion that the NFL made based on all of the other evidence, thus why Tom Brady ended up serving a 4-game suspension. Well, friend, I guess that settles it. But you know what? I still think that Tom Brady is the greatest quarterback of all time. So if you liked this video, make sure you don't miss out on future videos by hitting the subscribe button. And if you can think of a topic that you'd like me to cover in a future video, go ahead and leave a comment below.